All right, so I'm sure a lot of you were looking at the previous example I did, and you saw the fact that what I did was completely remove the idea of kind of sequence or ordering of words, right? And what I did was just throw everything in a bag, and I said, all right, we're just going to keep track of the fact that we have, three A's, or we have four thes, or seven Tims, right? And we're just going to lose the fact that, words come after one each other, and we're going to lose their ordering in the sentence. And that's how we're going to encode it. And I'm sure a lot of you are saying, well, why don't we just not lose the ordering of those words? We'll just encode every single word with an integer and just leave it in its space where it would have been in the original string. Okay, good idea. So what you're telling me to do is something like this. Tim is here will be our sentence. Let's say we encode the word Tim with 0, is 1, here is 2. And then that means our translation goes 0, 1, 2. And that means, right, if we have a translation, say like 2, 1, 0, even though these use the exact same number of words and exact same representation for all these words, well, this is a different sentence. And our model should be able to tell that because these words come in a different order. And to you, good point if you made that point, but I'm going to discuss where this falls apart as well and why we're not going to use this method. So although this does solve the problem I talked about previously, where we're going to kind of lose out on the context of a word, there still is a lot of issues with this, and they come especially when you're dealing with very large vocabularies. Now let's take an example where we actually have a vocabulary of say 100,000 words. And we know that that means we're going to have 100,000 unique mappings from words to integers. So let's say our mappings are something like this. 1 maps to the string happy, the word happy, right? 2 maps to sad. And let's say that the string 100,000, or the number 100,000, maps to the word, I don't know, let's say good. Now we know as humans, by kind of just thinking about, let's consider the fact that we're going to try to classify sentences as say positive or negative, so sentiment analysis, that the words happy and good in that regard, sentiment analysis, are probably pretty similar words, right? And then if we were going to group these words, we'd probably put them in a similar group, we'd classify them as similar words, we could probably interchange them in a sentence and it wouldn't change the meaning a whole ton. I mean, it might, but it might not as well. And that we could say these are kind of similar. But our model, or our encoder, right, whatever we're doing to translate our text into integers here, has decided that 100,000 is going to represent good and 1 is going to represent happy. And well, there's an issue with that because that means when we pass in something like 1 or 100,000 to our model, it's going to have a very difficult time determining the fact that 1 and 100,000, although they're 99,999 kind of units apart, are actually very similar words. And that's the issue we get into when we do something like this, is that the numbers we decide to pick to represent each word are very important, and we don't really have a way of being able to look at words, group them, and saying, okay, well, we need to put all of the happy words in the range like 0 to 100, all of the like adjectives in this range. We don't really have a way to do that. And this gets even harder for our model when we have these arbitrary mappings, right? And then we have something like 2 in between, where 2 is very close to 1, right? Yet these words are complete opposites. In fact, I'd say they're probably polar opposites. Our model trying to learn that the difference between 1 and 2 is actually way larger than the difference between 1 and 100,000 is going to be very difficult. And say it's even able to do that, as soon as we throw in the mapping 900, right? 99,900, we put that as bad. Well, now it gets even more difficult because it's now like, okay, well, if the range is this big, then that means these words are actually very similar. But then you throw another word in here like this and it messes up the entire system. So that's kind of what I wanted to show, is that that's where this breaks apart on these large vocabularies. And that's why I'm going to introduce us now to another concept called word embeddings. Now, what word embeddings does is essentially try to find a way to represent words that are similar using very similar numbers. And in fact, what a word embedding is actually going to do, and I'll talk about this more in detail as we go on, is classify or translate every single one of our words into a vector. And that vector is going to have some, n amount of dimensions. Usually we're going to use something like 64, maybe 128 dimensions for each vector. And every single component of that vector will kind of tell us what group it belongs to or how similar it is to other words. So let me give you an idea what I mean. So we're going to create something called a word embeddings. Now, don't ask why it's called embeddings. I don't know the exact reason, but I believe it's has to do something with the fact that they're vectors. And let's just say we have a 3D plane like this, and we've already kind of looked at what vectors are before, so I'll skip over explaining them. And what we're going to do is take some word. So let's say we have the word good. And instead of picking some integer to represent it, we're going to pick some vector, which means we're going to draw some vector in this 3D space. Actually, let's make this a different color. Let's make this vector say red, like this. And this vector represents this word good. And in this case, we'll say we have x1, x2, x3 as our dimensions, which means that every single word in our data set will be represented by 3 coordinates. So one vector with 3 different dimensions, where we have x1, x2, and x3. And our hope is that by using this word embeddings layer, and we'll talk about how it accomplishes this in a second, is that we can have vectors that represent very similar words being very similar, which means that, if we have the vector good here, we would hope the vector happy from our previous example, right, would be a vector that points in a similar direction to it, that is kind of a similar looking thing, where the angle between these two vectors, right, and maybe I'll draw it here so we can see, is small so that we know that these words are similar. And then we would hope that if we had a word that was much different, maybe say like the word bad, that would point in a different direction, the vector that represents it, and that would tell our model, because the angle between these two vectors is so big, that these are very different words, right? Now, in theory, does the embedding layer work like this? Not always, but this is what it's trying to do, is essentially pick some representation in a vector form for each word, and then these vectors, we hope, if they're similar words, are going to be pointing in a very similar direction. And that's kind of the best explanation of a word embeddings layer I can give you. Now, how do we do this though? How do we actually, go from word to vector and have that be meaningful? Well, this is actually what we call a layer. So word embeddings is actually a layer, and it's something we're going to add to our model. And that means that this actually learns the embeddings for our words. And the way it does that is by trying to kind of pick out context in the sentence and determine, based on where a word is in a sentence, kind of what it means, and then encodes it doing that. Now, I know that's kind of a rough explanation to give to you guys. I don't want to go too far into word embeddings in terms of the math, because I don't want to get, waste our time or get too complicated if we don't need to. But just understand that our word embeddings are actually trained, and that the model actually learns these word embeddings as it goes. And we hope that by the time it's looked at enough training data, it's determined really good ways to represent all of our different words so that they make sense to our model in the further layers. And we can use pre-trained word embedding layers if we'd like, just like we used that pre-trained convolutional base in the previous section. And we might actually end up doing that. Actually, probably not in this tutorial, but it is something to consider that you can do that. So that's how word embeddings work. This is how we encode textual data. And this is why it's so important that we kind of consider the way that we pass information to our neural network, because it makes a huge difference.